Hello! I was recently reading Bourbaki's theory of sets and absolutely burst out laughing when I got to their definition of the cardinality of a set, shown here below. In this video, I'd like to explain what this definition means and why I found it so amusing. Nicholas Bourbaki is surprisingly not well known, despite how influential they were to modern mathematics. Bourbaki was born in 1934 in France, and at a very young age sought to fill a gap in mathematical texts available in French. World War I was absolutely devastating to the French mathematical community at a time when mathematics was being rapidly revised and formalized, and it was Bourbaki's goal to produce modern mathematical texts in French. The plan started out simple, Bourbaki wanting to publish a treatise on analysis, something that could be used as a calculus textbook that reflected current understanding. But this project quickly ballooned in scope to a multi-book series called The Elements of Mathematic, with the goal of being logically self-contained and a solid foundation for the whole body of modern mathematics. And when I say logically self-contained, I mean it. Bourbaki wanted everything to be proved and every theorem used in every proof to be available earlier in the text, working all the way backwards to the foundations. The text even introduces a formal symbolic language with a strictly formal notion of proof to serve as foundations, and spells out how to translate all of modern mathematics to these strictly formal proofs via set theory. And Bourbaki is still publishing Elements of Mathematics to this day. Bourbaki's influence can be felt throughout mathematics, from the symbols we use for empty set, not in, implies, if and only if, to the words injective, surjective, and bijective. One of Bourbaki's biggest influences was a focus on mathematical structures, although honestly I'm having quite a bit of trouble making sense of their formalization of them. Now, I'm joking a little bit here. Bourbaki is actually a pseudonym under which a group of mathematicians publish, whose members have cycled in and out over the decades. But otherwise, this is true. Bourbaki's Elements of Mathematics starts with a book on set theory and foundations. Nowadays, if you wanted a solid foundation, you'd probably start by introducing first-order logic and the ZFC axioms on top of that. This is close to what Bourbaki does, but not quite. It's not quite ZFC set theory and not quite first-order logic as we know them today, but it's remarkably close. When discussing sets, one wants to, of course, discuss the concept of the cardinality of a set, a measure of how many elements it has. For instance, the cardinality of any set of 3 elements should be the number 3. In 1895, Cantor described the way of formalizing 2 sets being the same size, before set theory had been formalized, and even before Russell's paradox made it clear that it was necessary to formalize set theory. We say that 2 aggregates, m and n, are equivalent in signs m is equivalent to n or n is equivalent to m if it is possible to put them, by some law, in such a relation to one another that to every element of each one of them corresponds one and only one element of the other. Bourbaki uses the same definition, although now formalized with the concept of bijection. Instead of Cantor's vague by some law, Bourbaki defines bijections as sets of ordered pairs, x f of x, as we do today. But of course, when we talk about cardinality, when we talk about the sizes of sets, sets having the same size is a secondary property. We primarily want to talk about the size of a set, the cardinality of a set. If it's a finite set, the cardinality should be the number of elements, but we also want various infinite sizes, in case we need to talk about the size of infinite sets. And of course, one of Cantor's big results was that there are different infinite sizes that infinite sets can be. Nowadays, this is typically done with what are called von Neumann ordinals. We want some canonical set to represent all sets of size n, to represent the number n. And the clever idea is to use the set of all smaller ordinals, the set of all smaller numbers. For instance, 0 is represented by the empty set. There are no smaller natural numbers, and conveniently, this set is of size 0. So we're representing the number 0 by a set of size 0, and it's a very convenient thing to have. 1 is represented by the set containing 0, the only smaller natural number, and again, conveniently, this set is of size 1. 2 we represent by the set containing 0 and 1. Again, this is a set of size 2. And so on and so forth. Critically though, in ZFC set theory, the only objects available are sets. We can't talk about numbers or sets of numbers, so we have to expand out our construction here. We can still represent 0 by the empty set. That's fine. The empty set is doesn't have any numbers in it. It's just a pure set. But when we represent 1 as the set containing 0, we need to expand that out. There is no number 0 in set theory, but luckily we do have a representation of 0 in set theory. We represent the number 0 by the empty set. So 1 is represented by the set of the empty set, right? The set of our representation of 0. Similarly for 2, we need to represent 0 by the empty set, the set that corresponds to it, and 1 by the set containing the empty set, the set that corresponds to it. To get that 2 is represented by the set containing the empty set, that's our 0, and the set containing the empty set, that's our 1, and so on and so forth. In set theory, we don't talk about collections of things, boxes of things, boxes of numbers, but rather we talk about boxes of boxes, configurations of boxes within boxes, all ultimately empty inside, the interesting structure coming from how these boxes are nested inside each other. And the sets we've picked here wind up having this nice recursive, almost fractal structure to them. The clever thing is that we can continue this process infinitely. Once we've worked out sets to correspond to all of the natural numbers, we can construct a larger ordinal again just by taking the set of previous ordinals, that is, the set of all natural numbers, and we call this set omega. But we're not done there. Now that we have a new ordinal, we can again collect all of the previous ordinals together to create an even newer ordinal. That is, the set of natural numbers and omega, and we call this set omega plus 1. And if we toss omega plus 1 into the set, we get omega plus 2, and so on and so forth. And once we've constructed omega plus n for every natural number n, we can collect all of the natural numbers and all of those together to get omega plus omega, or omega times 2. And we can continue this process to produce omega times 3 and omega times 4 and omega times n in general. And thus, when we collect all of those together, we get omega times omega, or omega squared, and so on and so forth. And so much on, and so much forth. These ordinals were originally discovered by Cantor in the late 1800s in a dazzling display of accepting the possibility of infinities and just seeing where it goes. Hilbert was dazzled, at least. In On the Infinite, he described this theory as, I think, the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. And that was before von Neumann came up with this clever way of representing these ordinals in set theory. Note that all of the sets presented on this slide are countable. They all have the same size. They're all bijective with each other. We need to go so very much on and so very much forth that not even hyperoperations can save us before coming across an ordinal of a different size. But we eventually do, and just like all of the previous ordinals, it has this really nice recursive structure as a set. And we can keep going on spectacularly further. And now, once we have our notion of ordinal, we define the cardinality of a set to be the smallest ordinal that is equipotent to it. That's the same size as we defined before in terms of bijections. If we have a finite set, there's only one ordinal equipotent to it, specifically the one that corresponds to the number of elements of the set. But if we have an infinite set, it's a little bit trickier. Again, omega and omega plus 1 and lots of other ordinals are all equipotent to each other, but we pick omega, the smallest of them, as their common cardinality. Don't worry too much about all of this. The important part for this video is that we have this very specific construction for cardinality that mathematicians seem to pretty much agree on now, and that the cardinality of a set is some set with a nice recursively fractally structure to it. In the 1920s, Hilbert introduced the epsilon operator, a kind of choice operator. Given a particular formula phi, we write epsilon x phi of x as an expression representing some element x satisfying phi, provided there are any. Otherwise, it just represents some random object under consideration. So specifically, we can say there exists an x satisfying phi if phi holds of epsilon x phi of x, right? If there is such an x that satisfies phi, then epsilon x phi of x will be one such x. And if there isn't any, well, there's no hope that the element that it produces will satisfy phi. And because of this, we can rewrite first-order logical formulas with quantifiers replaced by epsilons. And Hilbert had hoped that studying the epsilon operator would allow him to remove quantifiers over infinite sets, this thing that he was very suspicious of, and hopefully by doing that prove that various bits of mathematics are consistent in some finitary way. Bourbaki take advantage of this in trying to construct a completely formal logic, something that can be understood and processed purely mechanically. Their tau is pretty much the same as Hilbert's epsilon, but with a different syntax. In order to avoid the difficulties of specifying how to deal with infix notation mechanically, Bourbaki used Polish notation. And in order to avoid the difficulties of variable scoping and the potential of using the same variable name twice, Bourbaki used a box and connection notation. So, for instance, they write some element of y as tau in box y, with the tau and box connected. It's something that can go in the box to make this true, and in box y is Polish notation for box is in y. The in goes to the front. Since this notation is an absolute nightmare to use, they immediately start using more familiar notation, with the idea that it's really shorthand for the more formal notation. I hadn't really seen the epsilon operator before I started researching the history of logic. It seems to have fallen out of fashion a little bit, but there's still some work being done with it to this day, and it's even featured in some modern proof assistants like Isabelle HOL. So now finally I can explain Bourbaki's definition of cardinality. They say that the cardinality of some set X is that some Z which is equipotent to it. Again, equipotent here meaning that there's some bijection between the two sets. Notice that they've already stopped using Polish notation and dropped the boxes with connectors notation. This is how they write at this point in the document that some Z that satisfies the following property. The important part with cardinality is that if two sets are equipotent to each other, they should have the same cardinality, and Bourbaki says, oh, that's the only thing we want. Just give us some arbitrary element that winds up being equipotent to both of them. And we'll call that their cardinality. So anyway, I just thought it was funny that while we have this really precise definition of cardinality that we use nowadays, which was available at the time. Gödel used it in his 1940 paper, where he proved the consistency of the continuum hypothesis. And this is 14 years before Bourbaki published Theory of Sets. Even though we had this precise definition of cardinality, Bourbaki just says, give us any set of the same size, and that's good enough for what they were trying to do. They needed just enough set theory to serve as foundations for their real goal of writing about mostly algebra and analysis. The reason why Bourbaki doesn't use our modern notation of cardinality isn't some grand mystery. Despite their desire to have a firmly founded series of texts, set theory, and in particular the theory of ordinals, just weren't that important to the group. So, thanks for watching. I find it really amusing to read historical mathematics texts. Bourbaki's theory of sets is maybe not the most accessible, since it does begin by introducing a brand new formal mathematical notation that's really hard to read, and then immediately dropping this formal mathematical notation for more familiar notation. But there's lots of really good stuff in there, particularly in the introduction. There's a real joy in seeing the germs of modern mathematical ideas that nowadays we take for granted, or in learning about completely unfamiliar mathematical ideas that have faded from popularity. Let me know if you have any questions or comments, or if there are any historical mathematics texts that you particularly enjoy. And be kind to each other.